Welcome again. I'm Greta Hassler with VECAN and VNRC, and this is my colleague Sarah Baer. So today, as you all know from signing up, we're going to be talking about the potential of thermal energy networks in Vermont. So one of the cleanest, most reliable and efficient, safest, healthiest energy systems is now on the table for Vermont. There's multiple ways to harness, share, and store thermal energy, and more innovations are emerging all the time. Excess heat from grocery stores, offices, data centers, ice rinks, and wastewater could be captured and exchanged between buildings here in Vermont, and the possibilities are really exciting. So today we're going to be joined by Debbie New, who leads the Vermont Community Geothermal Alliance, as well as two folks from innovative companies around the country, SHARC Energy and SHARC Energy, to hear about the work that they're doing and how it might work here in Vermont. And we're also going to have plenty of time for Q&A at the end. So feel free to put your questions in the chat as we go. And Sarah and I will be making sure to capture them. And we're going to aim to get to as many as we can at the end. So hopefully some great questions. I know everyone's coming prepared, thinking about how this technology could work here for us in Vermont. So without further ado, I'm going to turn it over to Debbie to kick us off. Thanks, Debbie.
Thank you. I coordinate the Vermont Community Geothermal Alliance, which is an umbrella for information sharing and for learning opportunities like this one. I really want to thank VNRC and VECAN for hosting the first webinar in a series. Today is part of a series of 3 lunchtime webinars. There's 2 more sessions coming soon, and there'll be information in the chat. I encourage you to register for those because it will be different information, different perspective on these energy solutions. I'm really glad that we're doing the first webinar for VECAN as a way of exploring the idea of network geothermal and other kinds of thermal energy networks in Vermont and opening up the possibilities for bringing these solutions here. It's really great to start with you and with Town Energy Committee specifically because you know what's needed and what's possible where you are. There's a lot we need to learn from you, so I welcome your input, and I'm really looking forward to our Q&A after our speakers. Today is an opportunity for us to be creative, to learn from examples of where these thermal systems are working, and to imagine these solutions in our own communities and our region. What are the opportunities, and what part could these networks play where you are? And we can get practical. How would you start the conversation? What would you need locally to help you put this solution on the table and put it to work? So first, what are we talking about when we talk about thermal energy networks? So what does thermal energy networks mean? So obviously thermal refers to heating, which we need a lot of in Vermont, but it also refers to cooling, which we will need more and more as the climate warms. So thermal networks can do both heating and cooling. The kind of energy we're talking about is geothermal from the ground, but it's also about capturing waste heat and using wastewater as a source of energy. We're also talking about networks because these are closed loop systems that link buildings. The ideas here are that we can exchange energy, not just between the ground and one building, but between the ground and many buildings or other thermal sources. And the intent is to balance thermal loads or thermal energy. So what if this is not district steam or combustion-based systems. So no gas and no biomass. Next slide. So let's just look at geothermal. You're probably familiar with it. So briefly, when you turn on your heat in your home, there's a ground source heat pump that delivers warm air and extracts cold air, like an air source heat pump. When you need cooling, the process reverses. The same heat pump delivers cold air and extracts heat, returning it to the earth. This energy comes from underground. It's from where the Earth's ambient temperature at about 500 to 800 feet is between 45 and 55 degrees. Water-filled pipes bring that temperature to your heat pump where it's concentrated into the hot or cold air you need. So geothermal energy is largely untapped in Vermont. There are some large buildings that have it, Champlain College, other schools, some businesses, like one that I visited, which is a little bit more of an industrial system, and we have a picture of that here. You may know of other examples. It's also a choice for individual homes, but it's not affordable that way, and it's not equitable. A network system can be affordable, equitable, and more efficient. For example, in a town center, buildings can be connected to vertical bores, which are like wells, that are linked by horizontal pipes. And these form the closed loops I mentioned earlier that exchange temperature with the earth and share it between buildings. This excess heating and cooling isn't wasted, but it can be exchanged efficiently between them. These loops can grow over time, so you don't have to do everything at once, but you can start small and actually build a network. There's more to say about the needed workforce, financing, and policy solutions to implement these systems in Vermont. We're working on those, and we can talk more about those later. But first, I want to make sure that we have time for our speakers. So I'm excited to welcome Yannick and Aaron. Each represents a company with innovative ways to maximize how we heat and cool our buildings. First, we'll hear from Yannick from SHARC Energy about her company's approach to geothermal networks.
Thank you so much, Debbie. Hi, everyone. Great to meet you all online. I'm so grateful to be here and share what we're working with in different communities and being able to share that with Vermont. I do have a few slides, so let me put them up here and make sure that everybody can see them. So a little bit about myself. Let me do a quick introduction first. Like Debbie said, so I'm Yannick. I'm a geoenergy solutions consultant with SHARC Energy, and I'll talk a little bit about our company in a bit. My background is mechanical engineering. I studied at UMich, Michigan, and I've been with our mothership company, as we call them, SLB. Celsius is a venture of SLB. I've been with SLB for 14 years now in various capacities, started as an engineer, and I moved into project management roles, and I was HR manager for our research center in Boston for a bit. And I recently transferred into SHARC Energy last year, and I've been pretty much blown away by what our team's able to do. So let me share a little bit about what geothermal can do for communities and how the technology has developed over the past few years. So why do we start this whole looking at geothermal in the first place? As many of you probably already know, a lot of the world's carbon emissions come from the building heating and cooling of our communities. And in the world, this right now accounts for about a quarter of the CO2 emissions. And for Vermont is no different. Just like we are located in Boston area, we're actually like Vermont, slightly above the US average, which is also about 25%. In Vermont, in 2018, when the community did a study, the building thermal accounts for about 34% of the carbon emissions, greenhouse gas emissions, overall, including the total emissions. So that's why we're looking at it. We want it to be able to utilize the technology that's available and then invent advanced technology to complement that, so we can find a sustainable way to heat our buildings and cool our buildings during summertime. Now, we hear about geothermal energy a lot these days. Why geothermal energy? Some people ask. What is all the big deal about geothermal? There's a couple of different cool things about geothermal as a technology. Overall, it brings comfort to our buildings. Unlike some of the other technologies available out there, geothermal can be invisible virtually, if you elect it to be. Once it's installed on a building or in a community, it could be most of the equipment's either housed indoors or underground, and it's not something that can be seen. However, it can be made possible. And I'll show some pictures of what we've done for a few projects. But in most cases, it could be aesthetically pleasing. It is quite effective compared to another very common technology, air source heat pumps. Usually ground source heat pumps are about 3 times as effective in terms of heating and cooling capacity. It is extremely quiet. There's no machines or equipment that usually sits outside of the window that runs during the day, and it is controllable. It is also quite a resilient technology. And geothermal, because of the fact that it sits under the ground for majority of its installation, it's sheltered from natural environments, right? So we don't see those equipments that are outside exposed to snow, to salt. As we are right now, we see a lot of salt outside of Boston. It is snowing. So it is kind of enclosed in that environment. It's also reliable because it's not intermittent. Ground is always going to be there. The earth is always there to capture and release heat. So that resource is running 24/7 as we need it. And geothermal is a great technology to couple with other technologies out there. It doesn't have to work by itself. If we're looking at making things even more cost efficient or even more environmental, there's projects out there that are utilizing geothermal being coupled with solar energy, wind energy, or SHARC, which I know Aaron's going to talk quite a bit about as well. They couple well together. So together, it works to make our environment even more sustainable and more efficient. And Debbie talked about network geothermal. Geothermal works on different scales. We see single buildings converted to geothermal, which can be costly, like Debbie says. But then the larger we grow this technology, the cost effectiveness also grows with it. So we now are seeing university campuses deploying geothermal. We're seeing communities looking at geothermal projects as well. That captures both residential and commercial buildings altogether. So it has some flexibility. And a good idea is to sometimes to start small. It could be a cumbersome project to look at. Let's say we're looking at a whole city, which you don't have to do it all at once. And that's one of the beauty of geothermal, is to start phasing projects. I see communities who start with a single neighborhood of maybe 10, 15 houses with 1 or 2 public buildings on site, and then eventually grow that into larger communities in different phases throughout the years. We started with geothermal with the whole idea of sustainability. So really that captures all of it. It reduces CO2 by up to 90%, and it doesn't produce any heat island effect. So there's no hot air being pumped out of a system into the environment. All of that is operated in a closed loop environment. So when you have community buildings that are closely knitted together, we're not continually contributing hot air into the outdoor environment. So that's a bit about geothermal in general. Celsius Energy, who are we? We are part of a larger organization called SLB. SLB has been around for about 100 years now, being the world's leading technology provider for the energy industry. And within the last few years, the focus on shifting from the traditional oil and gas energy industry into more sustainable and reliable energy has become a huge focus within SLB. Celsius Energy is a venture of SLB, so they're our mothership, and we are just a part of their green energy pie, so to speak. As a whole, SLB operates in about 120 different countries right now, with about 100,000 employees working all over the world, creating new technology. So we're excited to be part of it, and we're also very fortunate to be able to utilize a lot of the technologies SLB has developed over the years for the energy industry to our advantage to shift sustainable heating and cooling. So talking about different scales, most of the projects that we are involved in are usually on the larger side, stuff like network geothermal, for example, or campus geothermal. Right now, we're working on a project with Yale University on converting part of their campus from traditional gas boilers to geothermal. And on a more larger scale, I talk about communities. We're also working with a utility company on converting part of Massachusetts, a town in Massachusetts, into kind of a group network geothermal project as well. So that's all variations of scales. And another beauty of this technology is it can work both on new buildings as well as existing buildings. On new buildings, of course, it starts with the design and the installation of new equipment. But if there's already existing buildings, for example, community projects, most of the time we're looking at renovations of buildings that have been around for many, many years. And that goes into converting existing equipment into geothermal equipment and utilizing some of the existing loops that are already buried underground for other types of utilities. So the conversion, it doesn't have to be a complete ground haul, depending on what the situation is. So that's another beauty of that. Regardless of the size of the project we're looking at, right? most geothermal projects usually has 3 main pillars built into it. And that starts with the underground heat exchanger. These are the wells or the boreholes that are drilled into the ground so that we plug the building into the ground. And that's the part where we're extracting or taking energy to be put into the earth, or extracting energy from the earth. And we kind of think the earth as a giant battery in a way, if you will, where we are during wintertime, we take the heat that the earth core is constantly putting out to the ground, and then using that to heat our buildings. But then during summertime, we just do the reverse. We take the excessive heat that's above Earth's surface in our environment, and then we inject that into the earth. And the earth operates as a battery. It stores that heat until we need it again next winter, so we can extract it back up for building heating and cooling. So the underground heat exchanger are these well bores with the closed loops that circulate the fluid to transfer heat. And then the next part of it will be the connected technical room, which is where usually the heat pumps are housed indoors, either in a basement or in a side room or a utility mechanical room. And that technical room connects the ground to the building. Then the last pillar, which we are working at, is an intelligent performance management system that is one-of-a-kind technology that allows whoever's utilizing this technology in your communities or in your buildings to digitally observe and monitor and optimize the solution. So it's a digital control panel, if you will. So in the projects that we've carried out in the past, we've seen the effectiveness of these systems. In terms of heating, we're able to reduce carbon dioxide by up to 90%. And I talked about the no contribution to heat island effect. Cost-wise, it's also a great investment long-term. In terms of energy reduction, because we're using the heat from Earth and or heat that we put into the earth for storage, we're reducing electricity costs by quite a bit. And on average, I'd say it's about 60% reduction in terms of energy usage, and a little sometimes higher, sometimes lower. And in terms of OPEX for the building, you're also reducing costs there by on average about 40% because you're not using as much electricity. And the maintenance is lower. It's a very simple solution as well. And one thing about Celsius is we've advanced our technology to the point where we're able to reduce the amount of surface space that's necessary to install these systems. And I'll show you a picture really quickly to showcase what I'm talking about. So in a traditional geothermal system, as Debbie mentioned, usually we would drill boreholes into the ground. And majority of the times, these are either drilled vertically, or it could be horizontal loops that are laid out in an area. And these are great solutions. However, there are a couple of downfalls with this. One is the amount of space it takes to install a system, especially for larger environments, like, for example, a community or for a large commercial building. It takes a lot of land. And because we need to connect all those boreholes together. And once that land is scraped for geothermal installation, we're not able to utilize that land for building in the future or for future development. So what we've decided to do is we've created a technology where we're able to do directional drilling that allows us to reduce the amount of surface footprint it takes to install the system as effectively for the same size building. And this frees up the rest of the land for if there's other constructions going on at the same time for other reasons, you can use the land for that, but it also frees up the land for future real estate preservation if you need to utilize that land for another reason. So I always say a picture speaks 1,000 words, and I like to show some real job site pictures. And I think you can maybe hopefully appreciate on the left-hand side is a traditional installation of a vertical geothermal space for the building that you see behind it, the brown building. And then on the right-hand side, where this is a project that we carried out about 2 years ago, the parking lot to the left side of the street that you see is essentially the amount of space that we will need for the installation throughout the entire project. And it's for a building slightly larger actually than the building that you see in the left-hand picture. So it reduces space by quite a bit. And because of that, we're also reducing the amount of plastic that goes into the installation, because we no longer need all those horizontal pipes that connects those vertical boreholes together and then lead it into the building. So that reduces also the amount of water that's necessary for drilling, and we reduce the amount of total number of holes that needs to be drilled. All of this added together reduces your total cost for installation, which is a huge, huge factor, as we know when we look into geothermal installation. Most of the cost for a geothermal installation really comes from the drilling aspect of it. So the more wells that we drill, the cost goes up exponentially versus the material used. So if we can reduce the number of well bores, we reduce the cost effectively. So that's a little bit on the hardware side. Without monitoring and without understanding how your system works or how the installation works, it's really hard to optimize the design, and it's really hard to optimize the system, which is what we think the industry is lacking today on the market. So a solution that we brought forward is using the technology SLB already has. Thankfully, they've been in the industry drilling and trying to characterize ground for the past 100 years or so. We're able to borrow that technology to advance it for geothermal. And what we're able to do is, while we're installing the loops, we can characterize the ground to see what the actual heat transfer capability of the ground is at various stages of the ground, instead of a one-point capture, which is what the standard is in today's industry. Because we're able to know what the different levels of the ground allows the heat transfer capacity at different various stages of the ground is, we can then design the solution to optimize the system. So we don't over drill. We don't have to drill deeper than we have to. We don't interrupt the ground that we don't need to interrupt. And we don't have to spend extra money to drill a deeper hole if we don't actually need the deeper hole, right? So we don't over engineer. Another aspect of it is knowing where you're drilling at all times, because the last thing you want to do is to run into a different system underground or run into another borehole. So it's important to understand where you're drilling and capture that information statistically at all times, which is what we do in our operations. Once the system is installed, usually you'll see gauges installed at different parts of the system to capture the pressure of the liquid that's just going through your loops, or to capture the temperature of the water. And that is all great, but it doesn't provide a holistic picture of how your system's actually operating. So having some sort of a digital solution that allows you to see exactly how much energy you're extracting from the ground and how much energy you're using in the buildings can over time give an idea of whether or not your system's operating at its peak proficiency. And that's really important when you're thinking about installing a geothermal system. Consider that aspect of it as well. So one of the things that we do put out is this digital dashboard, if you will, that you see on the right-hand side in the middle of the slide, that gives you an idea of how much energy you're extracting from the ground versus how much energy, let's say if you have a complementary system installed in the same area, how much energy is being extracted through that secondary system. And then lastly, another consideration when you're thinking about installing a geothermal system is the various partners in this whole process that you will be working with. So typically there will be a company working on the drilling aspect of it, a company working on the design aspect, another company working on, let's say, the ground loop installation, and then the heat pump, and then the digital monitoring dashboard aspect of it. At Celsius, we can turnkey the entire solution so that it would be one partner that you go to and one partner that delivers the solution at the end of the day for accountability reasons, but also for efficiency, to avoid some of those errors or downfalls from handling between different parties who are working on a large project like this, especially when we're talking about community geothermal.
Yanning, there's just about 1 more minute before we turn it over to Aaron, and I'm seeing a lot of questions in the chat. It'd be great to get to. So do you want to show a couple of examples?
Yes, absolutely. And Debbie, do you think, should we answer the questions at the end, or would you like me to answer them during during
We'll do questions at the end.
Okay, sounds good. All right. So one thing I did want to mention, I understand I have about a minute left, is there are a lot of financial support out there available for geothermal as well. Because I know when we look at geothermal, cost is usually a big question for people. And there's different incentives through federal government and through local state agencies, as well as private financing. Like, for example, at Celsius, we do financing for projects as well. So there are different aspects to take into account when we're thinking about these systems. I do have a slide with a few different resources that I think you'll find helpful for anybody who wants to learn more about geothermal and how the financials might work out. So I'll leave them here. There's some videos about installation in case you're curious to see a real building being converted as well. And I understand that team's going to share that later on, so feel free to dig into them.
Great, so we can hand it over to Aaron to talk about thermal energy from wastewater.
Thank you.
Thanks, Yanni.
Thanks, Yanni. And that was an impressive presentation. You've definitely set the bar high. I'm going to share my screen. I've truncated my normal presentation as much as possible because there's a lot of technical slides that I'm going to blow past because now's not the time. I'm opening up the invitation if anybody ever wants to do a deep dive into wastewater technology and how our systems work. Happy to do it. I just want to try to keep this as high level as possible and see how we can, help you guys conceptualize wastewater energy transfer, in your area. So let me see about sharing my screen. So just a quick download on SHARC. We are a Canadian company. I live in New York. My name is Aaron Miller. I'm the Eastern Regional Manager for SHARC. I should introduce myself. My apologies. I handle everything east of the Mississippi and up into Eastern Canada. We are based just outside of Vancouver, British Columbia, in a small industrial town. We were founded in 2010 by a bunch of really smart people. The mythology is that Lynn Mueller, our founder and the inventor of the technology, he's got 200 patents. The guy's a genius. And he was semi-retired, sitting at home, and his wife was like, listen, you need to get a hobby or I'm gonna throw you out. And he had 2 teenage daughters at the time who were taking half-hour showers. He was trying to fit, and the light bulb went off. Necessity is the mother of invention. So he came up with the SHARC technology. Our first product, which is named the SHARC, rolled out in 2011. And I'm gonna do a quick dive into both technologies in a bit. And then we introduced our PIRANHA, which is our standalone. It's basically a water-to-water heat pump, but instead of using condenser water, we're using wastewater as the energy source. We introduced that in 2016 and then refreshed that in 2019 with a secondary connection. So we can not only use wastewater, but if you've got a cooling source in your building, we can actually take that rejected heat, run it through our system and make potable hot water as well. So the reason why, again, this is kind of this slide basically came out of Lynn's experience. Roughly 50% of a building's total energy demand is from thermal needs, and that's heating, that's cooling, domestic hot water. And those numbers are only rising as Debbie mentioned before, with climate change happening, we're getting more extreme swings. So heating and cooling are only going to get more challenging and more expensive if we continue with along the typical path. And the reason why, okay, this is part of the value prop for wastewater energy transfer. The average person uses roughly 30 gallons of hot water a day at 120 degrees. And what that means is you've got 45, 50 degree water, depending on your region, coming in from a well or from your city, and you heat that up through some methodology up to about 120, sometimes even higher. We touch that water for seconds, and then it goes down the drain, it's out, and it's just gone. So that delta between, from 50 up to 120 and then down to 70, because we found that no matter what the region is and no matter what time of year, generally speaking, out of a multifamily residential building or your typical residence, wastewater is exiting the building at 70 degrees. So what we're looking to do is capture that energy before it goes out to your septic tank, to your sewer, what have you. And what's great about our systems is we can produce up to 140 degrees, sometimes a little bit higher. So beyond just domestic hot water, we can make processed water. I'm looking at a bagel factory right now, a glass factory, They use a lot, they need a lot of hot water, and they make a lot of hot water waste. It's an ideal situation for us. And our system is unique from other wastewater energy transfer systems in that because our system is sealed, there's no odors. You can work inside of a building, and we can deal with black water, gray water, sanitary sewers, lift stations, wastewater treatment plants. We don't care. If you've got wastewater, it's got energy in it, and we can capture it and repurpose it. It's really quite brilliant. Why wastewater? It's a limitless source of energy. People flush toilets, run their dishwashers, take showers, wash a machine all year round. And as I mentioned before in the earlier slide, no matter what time of year, we've got consistent temperature on that wastewater. Even running through a sanitary sewer, let's say in Burlington, even on cold winter days, because it's underground below the frost line, it stays pretty consistent. And I've got some interesting slides from some Washington, DC data we captured, where even on snowmelt days, there'll be massive inrushes of flow and a momentary drop in temperature, but not enough to make a difference. So that wastewater is consistent throughout the year. And with all this new design of buildings, building envelopes are getting better windows, better walls, better roofing materials. So the one area where buildings are still losing energy is out that wastewater line. So by capturing that wastewater, we can reduce the energy losses from the building. We're using that energy to put back in the building. So we're dropping your operational costs. You don't need to use as much fuel now to heat, cool, and make domestic hot water. And that also translates into greenhouse gas emissions reductions. And I don't know really what's happening in Vermont just yet, but I know in New York, where I live, local law 97 in the city, they have massive carbon taxes, like right on the horizon, like massive taxes. So the built environment is freaking out. And we're seeing that these carbon taxes are starting to spread out across the country, Washington, DC, Chicago. So if it's not in Vermont yet, I suspect it will be coming soon. And the good news is, from the carrot side of things, there's strong market demand for heat pumps and for electrification. So that translates into local and federal legislation that includes free money and incentives. I've got a slide on the IRA, which I know Yanning touched on briefly earlier. And there's also utility incentives. Again, they're coming, and as the utilities become more hip to this technology, the incentives will also follow suit with more sophistication, more prescriptive and custom measures that I can help you dive into. So these are the two technologies that we sell, the PIRANHA and the SHARC. And I tried to create a slide that showed a continuum of basically small to the PIRANHA, larger to the SHARC. And it's not just building size, it really comes down to your flow rates. So the PIRANHA is really designed for a standalone building, right? The SHARC can be used for a standalone building, but a much bigger one where it really, where it shines and the magic really starts to come to fruition is when you can tie it into a campus, a network, a sanitary sewer, a geothermal field. We pair beautifully with geothermal. So I'm looking forward to discussing that with you guys. But as you can see, the through line for all of these building types is they use a lot of hot water and they make a lot of hot water waste. So apartment buildings, hotels, hospitals, microbreweries, car washes, and commercial laundries are brilliant for us. Commercial food production, and you can see district energy, which again is what this is really all about. And I'm convinced, and I'll discuss this in a little bit, that that's really going to move the needle for us as far as decarbonization to scale. Going after these individual buildings is great. It has to happen. I do it every day. But what's really going to make a difference and what's going to help us achieve those very lofty and, some would say a little bit pie in the sky decarbonization, electrification goals is to start doing things on a district level. So we can discuss that in a bit. This is the PIRANHA. It looks like a small generator, and it comes in three sizes, the T5, the T10, and the T15. And that corresponds to a heat output. Just like if you were buying a natural gas boiler, they come in different sizes. So we have small, medium, and large. And the great thing is they're modular, so we can, depending on the building characteristics, we can put two T10s together if that's what you need. So we have and again, this is something that I can dive in with you guys individually, but we have a project intake sheet. Tell us about your building, tell us about your project, your campus, what have you. And we take some really high level data, and it really comes down to what's your wastewater flow, like how much wastewater are you making, what's the temperature of it, and then on the demand side, what do you need? How much hot water at what temperature and for how many hours in the day? And then by looking at that, and Debbie mentioned that whole load balancing, by looking at both sides of the equation, we can properly size a system, and that's really the long and the short of it. And I've got a whole team of really smart people, and they're all Canadian, so by law they have to be nice, which is great. So happy to walk you guys through any specific applications. That's again, it's what I do for most of my day. And just a little technical information here. Your typical electric resistive heater has a COP of 1, a coefficient of performance. That means 1 unit of energy in, 1 unit of heat out. The PIRANHA, we are seeing COPs of 3.5 or even higher, meaning you put 1 unit of wastewater energy in, and we're getting up to 3 or 4, sometimes even higher, 5 units of heat out of it. And the HC model, the one I mentioned previously, that has that secondary connection to a building cooling loop, we can see COPs up to 8. So you can imagine just the overall efficiency is through the roof on these things. So it's great. And we're using wastewater. It's nasty stuff. It's toxic. So we use an NSF 372 rated brazed plate heat exchanger, which all that means is you've got complete separation between the wastewater side and the potable water side. There's never any cross-contamination. So it's completely safe to use inside of a building for potable hot water. And we're using R513A as our refrigerant. It's got a 56% lower global warming potential than the current industry standard. Refrigerant technology, man, we could spend hours talking about the politics of it, but we're trying to stay ahead of the curve. So we've got a highly efficient box that also uses a what we think right now is the best refrigerant available on the market as far as from an environmental standpoint. And as I mentioned previously, it's completely sealed, so it's odor free. You can put this in your building. You don't have to worry about smell. This is a line diagram real quick. I'm gonna try to keep pace with these technical slides. This is what a typical PIRANHA looks like when it's installed. There's a wastewater holding tank, which acts as a thermal battery. So for a typical apartment building, there's usually one sanitary outflow. We intercept that outflow and side stream it into a holding tank, again, sealed, vented, so there's no smell, and that acts as our thermal battery. The great thing about it, calling it a thermal battery, is it now really makes itself available for the investment tax credit from the IRA, because now you're dealing with thermal storage. It's a battery, and batteries the government understands. Wastewater energy transfer, not so much, not yet. We're getting there. So we capture all the energy in this wastewater holding tank, and then pump it, solids and all, through the PIRANHA, extract the energy. There's a tank inside there that's designed in such a way that there's no clog points. It handles all the solids. All the heavy stuff falls to the bottom and gets flushed out multiple times a day on an automated system. And then anything that floats gets back sent into the overflow. So we can do what's called multi-pass. So we've got 70 some odd degree water here. We're outputting up to 140 degree water. So sometimes you have to run that water through multiple times to get enough energy out of it to go to make that hot water for your plant. But this is a tried and true system. We've had them on, in the market running successfully since 2016, and we're adding more and more on market as every day goes by. I wanted to give you guys some examples. This is a hotel in Banff National Park. It's the Canadian Rockies. There's no natural gas. From what I understand, the vast majority of Vermont doesn't have gas distribution. It's only up in like 3 counties, I think Debbie told me. So this kind of fits right into that Vermont modality. So the hotel was looking for energy efficiency opportunities. we shoehorned our Piranha into their laundry room. We literally shoehorned it in. And what we're doing is we're capturing the wastewater out of these 4 commercial laundry machines, excuse me, into a tank, which they have already on site, because laundry machines, they have to pre-capture it to let the lint fall out, what have you. So we pump all that warm water back into our Piranha and then fill this tank on the right-hand side here with hot water, so that the washing machines, when they cycle up again, they're using hot water that's being made from the wastewater coming out of the machines that they just ran. And the manager of the hotel told us that prior to the Piranha going in, his hot water boiler would have to cycle like every 5 minutes. We're now getting it to about every 35, 40 minutes it has to cycle. And as you can see, with a COP of over 5, we're saving them 6,000 gallons of propane a year. And I don't know what you guys pay for propane, but it's a massive savings for the hotel. And again, large GHG CO2 reduction as well. And here's a multifamily residential building, also in Canada. We shoehorned it against the wall in the mechanical space. And this is a really lovely building, 60 units. And we are able to help them offset their energy usage by over 9,000 therms of natural gas a year. And we've also, again, massive reduction in their CO2 emissions. And because of this was part of the overall building design, but we're proud to say it's LEED Platinum. And here's a quick snapshot of the energy savings from that multifamily residential building. We've knocked basically their natural gas costs down by $10,000 a year, and massive reduction in their CO2 emissions as well.
That's great. Aaron, do you want to just take 1 minute to finish up, and then we can get to some of the many questions?
Oh, wow. I got 1 minute?
Yes.
Oh my God. Well, then I need to get, so, wow. Shoot. I really wanted to get to this. This is the SHARC. This is the big boy. This is the system that's on a network level is really going to play well with Yanning's and geothermal. And I'll blow through this slide. Really is what it comes down to for scale. So here's Yanning's geothermal field, and this SHARC is connected to a sanitary sewer, right? Or some type of wastewater energy source, whether it's a lift station, what have you. We are now using the sewer system as an energy sink or source. So if we need to pull energy out, we can just take energy out of the sewer, run it through the SHARC into the ambient loop. Or if we want to basically take energy out of the loop and put it back into the sewer, we can reverse the flow of the SHARC and sink energy into the system, into the sewer. So in essence, like I said before, the SHARC is a rural, suburban, urban geofield. And we're able to pair up with a geofield, a new construction one. And as Yanning mentioned before, the upfront cost of boring those holes is massive. By using the SHARC tied between a sewer or some wastewater energy source and the geofield, we're able to reduce the number of boreholes by up to 40 or 50%. So the upfront cost of that project gets slashed precipitously. And just real quick, this is a project outside of Vancouver in British Columbia, the University of British Columbia. They carved out a portion of the campus, handed it back to First Nations. First Nations owns the land. It's a private-public partnership. And basically, private developers have come and built multiple buildings on this campus, and they're using the sewer, the municipal sewer line, to create an ambient loop. And then each of the buildings on the campus is using heat pumps to push and pull energy out of the ambient loop. So we're now using the sewer to cover, as you can see on the right-hand side, essentially 1.3 million square feet of conditioned space. So I didn't realize, and there's a lot of money free, the Inflation Reduction Act, as I know you guys know, there's money coming in to help you guys build new sewers, new septic lines. But in addition to that, our product, even though we're Canadian, our Piranha's manufactured in Bellingham, Washington. All of the SHARC components, the vast majority of them come from the United States. So we're eligible for the 30% ITC tax credit. And you can get a 10% kicker because it's domestic content. And if it's a low income development, there's an additional 10% tax credit as well. So funding options are there, and between this and utility incentives, we can really offset a lot of the upfront costs. And when you look at it over time, and this is where I see the future, and this is something I'd love to talk to you guys about. These projects can be daunting. The good news is there are large ESCOs, energy service companies out there with billions of dollars of capital that they want to deploy, and they want to come into communities and buy up the projects writ large, from design, implementation to commissioning, startup, and operations and maintenance. Buy the whole thing out. You guys don't have to pay a single dime out of it. And then what they do is they sign essentially like it's very similar to solar, like a PPA, a power purchase agreement. You sign a long-term utility deal with that ESCO, and they own, operate, and maintain the hardware and just sell the service to the community and at a reduced rate for what you would think you would have to pay for those same heating, cooling, domestic hot water services from a traditional fossil fuel plant, obviously with all the environmental benefits. So there are pathways to get these larger projects deployed with very little upfront capital costs, but with immediate advantages being enjoyed by the community right off the bat. So thank you. And again, happy to do a deeper dive. I blew past a lot of tech today. So thank you for the time. I really appreciate it.
Thank you so much, Aaron and Yanning. This is really great. And I'm sorry that this just needs to be a kind of an appetizer, a very small one on a small plate. But I'm really glad we have our speakers to let them share as much as possible with you. There are a bunch of questions and excellent points in the chat. And I think, Greta, you've collected some of them. So maybe we could touch on some and do very short answers, and then we can regroup and figure out what we might need for follow-ups after this hour. Clearly not enough.
Absolutely. Yeah, let's do a rapid Q&A so we can get to as many as we can. So first up, maybe a good question for you, Yanning. Can pipes that previously had natural gas in them be used for geothermal, or do whole new pipe systems need to be installed?
Absolutely. So I think that's an easy question. Thank you for starting me off with that one. There are actually a number of utility companies in the country and also outside of the US looking into using existing pipes that are buried underground for other types of utilities and converting them for geothermal use. So not to say that those pipes are ready to go as they are. Some might need some maintenance depending on the aging and the material that was used and the diameter, of course. Some might need a little bit of an upgrade. But overall, this is definitely one of the business models that many utility companies are looking into. So I think the potential is big.
Awesome. And then maybe while you're still unmuted, one more. Gretchen is curious about the price per ton for network geothermal compared to individual residential and commercial geothermal systems. Right.
So that's actually a great question, Gretchen. The short answer is it's difficult to say because it varies so much depending on what your heating versus cooling needs are and how big of an area you're looking to supply geothermal for. And also depending on, for the installation cost, what kind of ground you're looking at. Some grounds are hard to drill through and some are easier. But a lot of it really varies on your heating load demand for the building or the community. The range, I could give one, but it is quite big. Usually, people say for geothermal, it's anywhere between 2,000 per ton to 8,000 per ton. So that is a huge range. The variation is quite large. I think the best way to look at this is to do a study. And we do, for example, if a company or community is interested, or even a house is interested, usually what we would do is we go in there and we would do a study based on the heating bills of that facility or based on the square footage and how much occupation is there. And then we kind of do a calculation for that specific project.
Great, thank you. Debbie, this is more of a comment, but maybe you can respond. Bill says, I appreciate the focus and intent of this webinar, but disagree with the blanket statement that geothermal isn't affordable for individual homes. We will need both individual and network systems going forward.
You're absolutely right. And that's why I asked to bring this up, because so I apologize for making that statement. There's been so much focus in terms of affordable housing and prioritizing low-income housing for these systems. And so that's been my mindset. And you're absolutely right with the IRA incentives that Aaron was mentioning, 40% off for the entire system. That does make it affordable for some people, not many people in Vermont. So I'm trying to keep the cost issue up front and really look at using ESCO's utility models in order to make this accessible and affordable to everyone. So I wanted to address that. Thank you for bringing that up, and I will adjust my talking point on that.
Thanks, Debbie. Maybe a good question for Aaron. Can you talk about the payback time for a project like you're describing? And I know you were about to get into IRA incentives and all that good stuff. So maybe some talk about costs and payback.
Yeah, and no one likes this answer, but just like Yang said, it really depends. I was talking about that balance before. It all depends on your site conditions. I've seen our systems with paybacks as short as 2 or 3 years. I've seen them much longer. It really depends on how much energy we have access to and where we can put that energy. So like DC Water, one of our major systems down in Washington, DC, we're literally on a lift station, and we're dealing with millions of gallons a day. That project paid off in like no time, because they built a office building around the lift station, and we're using the wastewater in the lift station to heat and cool the building. And we literally pick up 97% of the cooling load from the building. And in addition to the energy savings, they no longer have to use their cooling tower like almost ever. We're now saving them 1.2 million gallons of fresh water a year as well. So it really depends. Simple payback, just like I always give this answer. If you're buying a boiler based on payback, it's a losing proposition. You buy a boiler because you need hot water. So when you look at the value stack of all the benefits and all the free money and the incentives and the tax credits, then we start, the payback looks really attractive. But simple ROI, it can look ugly, I'll be honest with you, but it really depends on the building. You know, we're finding that it's, as Yanning said, especially as we're getting to scale, these things are getting more affordable, especially because we've got utilities and municipalities, state and the federal government finally getting behind us, you know. So I'm sorry if that's not a satisfactory answer, but it's a real one.
And, you know, maybe when we're still on the topic of cost, and this could be for any of our presenters, but what upfront cost comparison to long-term cost comparisons have been done, and how can the high upfront cost be shared to convince homeowners to change to geothermal?
That's a good question. So the typical ROI for a geothermal system is anywhere between, we say, 5 to 10 years or so. Again, depending on really on what the need of, you know, your demand is for heating and cooling. I hope that helped answer the question a little bit with on the IRI front. I think also to kind of, Aaron pointed that out already, and I had a slide on it, so I apologize if we didn't have time to go over it, but there are a lot of incentives out there, not only on the federal level, right, with the IRA that allows you to get up to 40% tax credit back for these type of systems like SHARC or geothermal, but there are also sometimes state level incentives that we can cap on, or utility rebates for geothermal is another option that sometimes people could look into. And another aspect of it is for whatever your tax credit doesn't cover or rebates doesn't cover, financing could help. And a lot of the times what we see, just an example on the financial aspect of it, is with our clients who have financed their systems, the monthly cost, because the amount of energy that's used to heat and cool a building is lowered by so much, your electricity bill reduces by a huge amount, usually 40 to 70% energy reduction for your systems. And then you would pay a monthly system, just like electricity bill, you pay part of it for energy usage and then part of it for maintaining the system. So gas. So same for geothermal, with financing, you would pay a low monthly fee for that system while it's being financed, kind of like a mortgage. And that monthly cost for the system plus the low electricity cost usually is around the same of what typically people are paying monthly for their electricity bills. But then at the end of that financing term, once 15, 20-year, whatever contract you have with the financing firm is done, then the cost left is the low electricity cost because you've already paid up for the system itself. So hopefully that helps a little bit in terms of explaining how that works.
I would also add that a lot of people I've met in the thermal energy networks world talk about how you're buying all of your fuel up front. And in Vermont, we have a bill in front of the legislature. It's H242, and this can help towns and communities across Vermont access this. What it does is follows very closely a New York bill that passed the Senate unanimously over in New York last year. So it takes that bill and it makes it apply to Vermont. So it allows existing utilities to do these kinds of thermal energy networks, but it also allows other entities like energy co-ops, municipalities, homeowner associations, even businesses like a fuel dealer business that is looking to evolve into new ways of doing business, to become utilities, to access the utility model as a way of accessing the money that's needed for the upfront infrastructure and then recovering that amount back over time. So this is a way to have not just investor-owned utilities do this work, but also nonprofits and Vermont communities have a way of affording these systems.
Awesome. Well, we are just about at 1 o'clock. I want to be mindful of everyone's time and just say thank you so much to Aaron, Yanning, and Debbie for being here today and sharing all of your expertise. We have so many questions, so many great questions that we didn't get to. And so just know that this is the first of a series of webinars put together by Vermont Community Geothermal Alliance. So this is the beginning of a conversation. We can definitely share all of these questions and the chat with everyone. I just want to turn it over to our three presenters in case you have any final parting words for us, noting that we're at time here.
I would just say, please distribute my contact information to everybody and call me. Happy to really, this was a great conversation, and I look forward to continuing it. So thank you, Yanning. Thank you, Debbie. Thank you, Sarah and Greta. I appreciate this. This has been
Absolutely.
fun.
Thank you so much for the work that you guys are doing. This is awesome. Lovely to see this type of communication going on.
Yeah, thank you very much. And please sign up for Vermont Community Geothermal Alliance if you'd like to. There's a link in the chat. And let me know what your questions are that didn't get answered, and we'll do our best.
Sounds good.
Thank you very much.
Good.
Thanks, everybody.